Hi, this is question number 12 in chapter 7. The question reads, a 23 gram bullet is traveling at 230 meters per second. It penetrates a 2 kilogram block of wood, emerges cleanly at 170 meters per second. If the block is stationary on a frictionless surface when hit, how far does it move how fast does it move after the bullet emerges? So you can see here that I've made a sketch of what's going on here. We've got the bullet. The bullet is here, and it moves into the block of wood, but it doesn't stop there. So it's not an inelastic collision because they don't hit and stick together. So if I were kind of looking at this in real time here, it would look something like this. The bullet comes in from some distance, slows down, and then just comes out through this block of wood here on the other side. So now in my static representation of that, we can see that the velocity here is slowed down. The bullet exits cleanly on the other side. We know that the surface is frictionless. So it's a little bit different than things that we've seen before. However, we still know that the sum of the momenta in the system before the collision must be equal to the sum of the momenta in the collision after the collision. This is basically the law of conservation of momentum. I'm also given some other information in the problem. I know that the mass of the bullet is 23 grams. I know I'm going to immediately need to convert that to kilograms. So 0.023 kg is the equivalent of 23 grams. Let's go ahead and identify what we know in this system ahead of time. What is momentum in the system? Well, when I look at my before picture, clearly here the bullet has momentum. It's got mass and it has velocity, but the block does not. So kind of when I write that out, I'll say, well, I've got the momentum of the bullet. And to make this easy, I'm going to call the bullet object A and the block object B, just to kind of keep this neat and clean. So the momentum of object A plus the momentum of object B. I'm just being formal here, recognizing that object B has no momentum before the collision. And everything on the right-hand side of the equal sign is going to be the momentum in the system after the collision. Let's go ahead and take a look at that. Of course, it's easy to see that the bullet has momentum after the collision, but we should recognize that the block itself has momentum too, because now it's moving to the left. And so I should probably just go ahead and draw in another little vector here to say, well, we expect that to be moving to the left as well. So the block has momentum after the collision, and so when I write that out, I should have the momentum of object A after the collision plus the momentum of object B after the collision. Now I can't say that they stick together, so I'm not going to play that little game where the velocity of A and B after the collision must be equal to each other. That would be pretty crazy, by the way, if this block was moving to the left at 170 meters per second after the collision. That's not happening. Okay, so let's go ahead and write this out. I'm going to get mass of object A times the velocity of object A before the collision is equal to the mass of object A times the velocity of object A after the collision plus the mass of object B times the velocity of object B after the collision. And by the way, I should put a subscript here. That mass of the bullet is 23 grams. And they tell you that the mass of the block, which of course we're going to need, is 2 kilograms. So the block is much more massive than the bullet. Okay, I've got everything I need. I've got mass of the block B, I've got mass of the bullet A, I've got the velocity of bullet A after the collision, I've got the velocity of A before the collision. So I've got everything except my one unknown, the velocity of B after the collision. I'm simply going to rearrange this equation. Again, recognize that I'm not saying that VA prime and VB prime are equal to each other, because they are not. This collision is not inelastic. They don't hit and stick together. But I still can say that in any collision, regardless of type, that momentum is conserved. All right, let's go ahead and rearrange this equation. I'm going to say that MAVA minus MAVA prime is equal to MBVB prime. Now I'm going to divide both sides by the mass of the block B. While I'm at it, I'm going to factor out an MA just because that looks like fun. So I'm going to get MA times VA minus VA prime all of that divided by the mass of block B, and that expression yields the velocity of block B after the collision. Now let's go ahead and just substitute some terms in. The mass of block A is 2 kilograms, and in the parentheses here I've got the velocity of the bullet before and after the collision. That's going to be 230 minus 170 meters per second. And finally, I'm going to divide all of that by the mass of the block. Oh, I've made a mistake here. Check this out. So the mass of block A right here, that's not the block, that's the mass of the bullet. It's not 2 kilograms. So I'm going to have to fix that before I plug things in. This is the mass of the actual bullet. So that's going to be that 0.023 kilograms. Okay, so now that I've made that correction, I'll put the mass of the block B down here on the bottom. That's going to be 2 kilograms. And when I run that through my calculator, I'm going to get the velocity of block B, and it's going to turn out to be, after the collision, 0.69 meters per second. Now, a quick note about signs. The velocity of block B after the collision is clearly to the left. We've kind of indicated that in our sketches. But it's also important to recognize that we should have probably established a sign convention right out of the gate at the beginning of this problem. So I'm just going to kind of sketch that down here in the bottom left-hand corner. So here's my traditional XY axis. And if I were playing by rules that were not changeable, then anything going to the left would be negative and anything going to the right would be positive, which means that all of these velocities that I had put in here should have been negative. However, it's pretty clear to me that since everything in the problem is moving to the left, let's make it easier for myself and call left positive, scratch that out, and make to the right negative. So that way everything based on this convention I've drawn here in the lower left-hand corner, everything is positive, which means that my positive answer here means to the left. But it's important to give signs some consideration when you're doing these types of problems.